Hello and welcome to my channel. In today's lesson, we will consider the notion of a field in abstract algebra. We will start our lesson with a motivation. Let's consider that we want to work with certain objects in space, and these objects are arrows. Now, if we consider an arrow in this direction, we also want to look at arrows in reverse direction. So if we reverse the direction of this arrow, we get this other arrow. Now we want a convention for the directions of these arrows. So if we have an arrow moving in the forward direction and same arrow, we've moved it to the opposite direction, we use the convention that the forward direction is positive direction and the backwards direction is the negative direction. Also, these objects, we want to be able to scale them in the sense that if we have an arrow, we want to find fractions of this arrow. So if we have this arrow, we could consider half of this arrow. So half of your arrow. So if I call my arrow, let's say A, then we have half of it. But we could also consider scaling it above, beyond itself. So we could also consider twice of your arrow. So that means we want some objects which have some scalars, which we can find fractions in. But we also want to be able to add these arrows. So if we have this arrow and we have another arrow, we add them by what? Continuing with it. So if we have an arrow of this form, which was your half A, we can add this other arrow to it by continuing with it from where this one ended. So plus 2A. So we want to be able to add these two to get a certain number. So the numbers that we are considering, we should be able to add these numbers and we want to get some other number that will give us another object. Now, so these numbers that we have here should have certain properties, and these are the properties that we need in order to get these arrows to be able to be added and scaled. These properties are what we call the properties of a field. Okay, so for a field, we want to be able to find scalar fractions of the scalars. Okay, so fractions of the scalars, because in our arrows, we want to be able to either scale up or down. They should also have negative numbers because we want to look at reverse directions of our arrows, but we should be able to add them. So this is why we get all the axioms we get for a field. We want scalars that you can divide, you can add, you can subtract. But finally, too, we want that if we consider this arrow moving in the forward direction, same arrow moving in the backward direction. So if you want to add these two arrows, so if we go forward direction, which gives us A, and we want to add it to the backwards direction. So forward direction ended here, and the backwards direction, if you want to add it to the backwards direction here, minus A, it means that we started from here and ended here, which means we did nothing. So you want a notion of nothing, which we will use a convention as what? 0. So in this scalars, so you want something that has to do with what? Nothing. So these properties all come together to give you what we call a field. Now let's write it in terms of a reverse direction. Now let's define what a field is by seeing the motivation for learning fields. A field is a set K, not just a set, a non-empty set, together with two operations, addition and scalar multiplication. We saw that we wanted to be able to add the arrows, we wanted to scale them. So the scalars belong to this set, non-empty set, which we call field. We want closure in the sense that if you pick two scalars, R and S, in this set K, and you add them, you want to still get a scalar in this set K, which means that when we're looking at the arrows, when we were adding fractions of arrows to the other, you want to get another fraction or number which is still in the set K. But it could happen that you could have 3 or more scalars R, S, P that you want to add. Now you can only add 2 at a time. So you can either add the first two and then your last scalar P, or the last two and the first. Now you want that irrespective of the order, you want it to be the same. And the equality here is what we call the associative property. But we wanted a notion of doing nothing. In this sense, the identity and the addition, where when you add and you reverse, you want it to be the same. So under addition, you want this unique element 0, which we refer to as the identity element, such that for every element R in your set K, if you add R to this identity 0, it does nothing to it. You still get back your R. Whether you add it from the right or from the left, it still remains the same. That's what we call the additive identity. But we wanted a notion of reversing direction. So if you had your arrow in this direction, you wanted to reverse it in the other direction, where we had the positive and the negative direction. So for every scalar, we want its reverse or its inverse or negative to belong to the set K. And that means that for every element R, you want its reverse, which we call negative R, to belong to it, so that if you take that number and you reverse it again, it means that you did nothing, okay? Whether you started with the reverse first or the number itself, it still results in nothing. Now, if you have your set, non-empty set K satisfying all these four, but in addition, we want that the order in which we add our arrows not to matter. So that if we have our scalars R and S, we can choose to add R before S or S before R. We want the order to remain the same. And in math, we call that a commutative property. So if for your non-empty set K under addition, if all these 5 axioms of closure, associativity, additive identity, additive inverse, and commutativity is satisfied, then we say that your set K under addition is an abelian group. Now, if we consider the second operation of scalar multiplication, if you can now consider your non-empty set K, but now we are omitting the 0 element, the do nothing element, then we want that if we multiply any two scalars, we still get a scalar. So you want a closure under multiplication, but you also want associativity because you could have 3 or more scalars that you are multiplying. And you don't want it to matter whether you multiply the first 2 scalars before you multiply the third, or the last 2 scalars before you multiply the first. You want it to be the same, and that's called the associativity and the multiplication. But you also want a notion of doing nothing when you are multiplying a scalar. So you want a unique multiplicative identity 1 belonging to your set, such that if you multiply any element in your set out by it, whether from the left or the right, it leaves the elements the same. But we wanted a notion of what? Inverse, in the sense that the scalars that we had, we wanted to find fractions of these scalars. So fractions in the sense that you want to find multiplicative inverses, so that if you have any scalar, you have another scalar, which is the inverse of it. But you can think of the reciprocal or the fraction of it, so that if you multiply that scalar by its inverse, it gives you back your multiplicative identity, whether you multiply it from the left or from the right. And finally, you want that your multiplication to be commutative, so it doesn't matter the order in which you multiply. So for all scalars, R times S the same as S times R. So that means that your set K, if you take out your 0 element, and the multiplication is an abelian group. So a field, in summary, a field has what? 2 properties, right? A field K is just what? You have a set, non-empty set K together with 2 operations, so that's what you have what? An abelian group, and the addition. And also you have an abelian group and the multiplication, of course, if you omit your 0 elements and the multiplication. Okay. Yeah, note that you have to omit the 0 element in your field. Okay. So that's what a field is. Let's move on to look at certain examples of fields. So scalars, you are thinking of numbers. When we learn numbers, one of the first number systems we learn is the natural numbers. So think of counting from 1, 2, 3, and so on. Will this be a field? Let's test and see. If you add two natural numbers, you get another natural number. Yes. If you have three or more natural numbers and you add them, will the addition be associative? Yes. But do we have the identity 0? Yeah. No, because we can see here that 0 doesn't belong to this set. So no, this is not a field because at least one of the axioms fails. Okay, good. This is not a field. Now let's look at another number system, which is the set of integers. Now, if you consider the set of integers, which we denote by Z, you just think of positive and negative whole numbers. So -1, -2, -1, 0, 1, 2, and so on. Now, in addition, yes, you have your closure, you have your associativity, you have your additive inverse, you have your additive identities. It will be commutative and addition. Now, when we go to the non-zero elements under multiplication, you have your closure, you have your associativity, you have your multiplicative identity, but will we have multiplicative inverses? Now, I'm asking, is there some element Q in Z such that if you pick an element 2 here, 2 times Q equal to 1. So that element Q will be a fraction, right? That fraction will be 1/2, but we can see here that 1/2 doesn't belong to this set. So there are some elements in this set that do not have multiplicative inverses. So this cannot be a field. So the answer here is no. So it means that this set here is not a field. Okay, so we've seen two non-examples. Now let's look at an example. So from integers, let's move to the set of rational numbers. So the set of rational numbers, you are just looking at what? The set of all fractions a over b, so that a and b are integers, with b not being 0. You can check the axioms and see that, yes, this would be a field. Now, if you consider a set of real numbers, then they also satisfy the axioms for a field. Let's look at a bigger set, which is the complex numbers. So you look at all numbers of the form a plus ib, where your a and b are real numbers, and I is just an imaginary number with I squared equal to -1. Then this is also a field. This is quite special in the sense that in algebraic geometry, you find solutions or roots to polynomial equations. And if you have a polynomial with coefficients from R, there are some equations that will not have roots being real numbers. But when you extend to the complex numbers, then all polynomials with coefficients coming from C will have roots in it. And we call that algebraically closed. So this is quite special in terms of a field. So the set of complex numbers is an algebraically closed field, which plays a very important role, especially when you are looking at what eigenvalues and eigenvectors, which we will look at later on in this series. All these examples here are examples of infinite sets which are fields. So that means they are very large. But can we look at some finite sets which are fields? Let's consider the 12-hand clock. We live in a 24-hour world, but we use a 12-hand clock. So usually when it's 1400, we say it's 2 p.m. Or we tell time by what? AM and PM. So AM means from midnight to 12 noon, and PM is from 12 noon to midnight again. Right? Now, how do we say that 14 is the same as 2 p.m.? We look at the remainder when 14 is divided by 12. And that gave us that's what 1400 is equivalent to what? 2 p.m. And in math, we call that modulo arithmetic. So modulo arithmetic, look at the remainder when you divide the resulting number by the modulo you are considering. So here we are looking at addition modulo 2. So if you have your sets containing 0 and 1, when you add two things, you look at the remainder when you divide it by 2. So 1 plus 1 is 2, but when we divide 2 by the modulo, which is 2, you get a remainder of 0. 0 plus 1 is 1, and the remainder is 1. 1 times 1 is 1, and so on. And you can check that this will form the axioms satisfy the axioms of a field. So this first example of a finite field. In general, if you have a prime number P and you consider the set ZP, which is 0, 1 up to P minus 1, and you consider additional multiplication modulo P, then this will be a finite field. The reason we are considering prime numbers is that if you consider non-prime numbers, then some things can go wrong. So for instance, if we consider Z4, which is the set 0, 1, 2, and 3, then 2 belongs to the set, but there's no element in the set that if you multiply by 2, you get 1. Also, 2 times 2 in this set is 4, but in modulo 4, when you divide 4 by 4, the remainder is 0 modulo 4. So even though 2 is non-zero as an element here, its product is giving you 0, which will not make the set behave nicely. So we call this zero divisors. So we call this a zero divisor. So it wouldn't satisfy the axioms for a field. One of the things that won't be satisfied is that some elements will not have multiplicative inverses. Okay, so this is a non-example of a field. So here we say that this is what Z is not a field. Good. So that'll be it for this class. We'll move to the next lesson where we'll consider vector spaces over fields.